Hello everyone, this is Professor Ma, and this is the introduction on the quadric surface or second degree surface. Quadric surface means second degree in x, y, and z. Okay. Equations. We went through the equation for plane, which is first degree. So now we're going to do the second degree. And the general method we're going to visualize the surface of a second degree equations is to look at a trace. Okay, and suppose the graph of the equation is this saddle shapes, and but we don't know what it looks like. Imagine it's invisible. But what we can do is we can take the intersections of planes. In this example, we're going to intersect with the plane x equal to c, and then I will get a parabola pointing downward. And that I call a trace, a tracer. A trace left over by a path by some animal. So I can, via this trace, via a whole set of trace, I can change the number c, so I can see a whole series of trace of lines, which are the outline of the shapes that I can, of the saddle, so that I can imagine what the saddle looks like. I can take this trace in different directions. Here's a trace in the direction of y equal to a constant. So these are the basic methods. And we're going to do this to the second degree quadric surface. That is, we're going to set one of the variable to be a constant. But if we have a second degree equation x, y, z, we set one of the letter constant, then we're left with two letters of second degree. So here, to remind students, here are what the graph looks like of second degree with two letters. Okay, conic sections, okay? In particular, these two are the same. Circle, it looks like basically the same, and they are the sum of two squares equal to a constant. And a single equations like that is a parabola. Then if it's a differencing of two squares, that I have hyperbolas. And the way we're going to the main way we're going to track the shape of the quadric surface is to establish these first. See if we have trace that looks like those. Okay. And if I have a function in the form z equal to f of x, y, then I can set z to be different constants. So when I set z to be a c, then I get the equations in x and y. Then I can graph that equations, and what I produce is the level curve at z equal to c. Okay, and here is a picture of the level curve of the devil's powers, and I just pull up the internet, and you can see. And here's the 5,000, 4,700. So indeed, everywhere around this curve is the 4,700 foot level. And if a functions, if I have a function given this form on z equal to f x y, I can then produce series of level curves. Then I can visualize what the surface looks like. And here, this corresponds to the surface of the devil's powers. So, for example, if I have an equation like that, no z squared, only a z, then I can attempt to put into a function form z equal to x squared plus y squared. Then I'm going to set z to be a constant. That is, I'm going to find the level curve. And this one will not have any level curve if z is negative. So I only get solution when z is positive. And in particular, I only get level curve when z is 0, 1, or 4. In particular, I get a bunch of circles. When z is 0, I get a point. And when z is equal to 1, I get a bigger circle, radius 1 is equal to 4, I get radius 2. Then if I stack these circles up, I get these cone shapes. Okay. The official name is not that important. You can look at in the books. Paraboloids. Okay. And those are the traces which we calculate. Notice on this computer-generated graph, we have these parabolic trace. Those are the trace with setting x equal to a number. For instance, this slice, this is the intersection between x equal to something and the surface. So in particular, if I investigate the trace with setting x equal to some number, and then I get the series of parabola along the YZ plane, and those are the curves, the parabolas, the layers of parabola, the trace in the x, setting x equal to a constant. So these are the general quadratic surface formula. So how do we approach to sort out which is which? So let me organize them a little bit. It turns out that most of them are pretty easy, and the only exception is that saddle points. Okay, I'll get to that. Why? Because every here you will see. Okay, this is the most important, the most fundamental one. That's a sphere or ellipse. That's the closed one, ellipsoid. The other, notice we all have sum of square, even including this one, because if I were to move these parts to the other side, or you can manipulate this into y squared b squared plus z squared c squared. We go to x squared over a squared minus 1. In other words, there is a sum of square in here. You just have to do a sign change, multiply across by minus sign. And that helps us in these 4 cases. That is because of the sum of squares. So here are some examples involved. Here's a summary of those equations. Here is the ellipsoid. A is the x-axis radius. B on the y square is the y radius, just like the case in xy. So I'll let it go. So this you should know by heart. You see, positive x squared, positive y squared, plus some more on z squared is equal to a constant. You know it's an ellipsoid. It's enclosed. Very important. It is enclosed surface. And now the other one enclosed. Okay. So this is the ellipsoid with the following axis. Okay. Now let's change one of the signs. So what happens if z squared is a negative terms? Well, move to the other side. And look at x squared plus y squared. Okay, that's a circle. And that circle has radius, the square root of this number. This is a radius. And this is always bigger than 1. So the radius is always bigger than 1. So when you select, so let's take a look at the, set z, the trace set z equal to a constant. And here they are. Okay, here is when z is equal to 0. Okay, then subsequently you get the equation x squared plus y squared equal to 1. In other words, right on x plane, you have the circle radius is 1. And as z gets bigger, for instance, if z becomes, I don't know, square root of 3, because y square root of 3, because it works out. So suppose z is equal to square root of 3, then you get the equation x squared plus y squared is equal to 4. then you will get a bigger circle at the level z equal to 3. And so this has radius equal to 2. And so on, so on. So, and since this is going to square the z, it doesn't matter which direction z is positive or negative. So on the negative side, you have exactly the opposite. Z equal to -3, you get the same equations. X squared plus y squared equal to 4. Okay. Hence, you get these rings of circles stacked together, but they come to a pinch point. You know, they become narrow in the middle. They look like the following shapes. Okay, this is the circle of z is equal to 0, x squared. These equations. They don't have this circle. Here they are actually functional ellipses. Continue. What if I have the two negative terms? So we arrange them into these fashions. Then we look at this again. We're going to get ellipses. Okay, if A and B are the same, then they are circles. Okay, you can treat them the same. If you want to look at the circles, that's fine. But this time, in order for me to get radius positive, z has to be bigger than or equal to c. Okay. So in order for z squared over c squared bigger than 1, so this would be bigger than or equal to 0. These conditions must be met. What it means is the graph has no trace. If you try to slide through a z at different level to see the trace, there's no trace for z until you get to z equal to c. Between 0 and c, there's no trace. So once you get to z equal to c, then you get a bunch of ellipses stacked up. So in this case, there will be two separate bowls, elliptic bowls, one up, one down. And they starting at a point over here. This point where it starts is z equal to c. And of course, and then the y is equal to a and b. Well, 0, 0, 0, 0, sorry, 0, 0 is a and b. Right now, it doesn't really make sense. Okay, the only solution is 0, 0 at that point. Okay, and the other is -c. And then, of course, I get a bunch of ellipses that gets bigger and bigger. Now, finally, we come to the equation. Oh, and then there's what were the equation z squared y squared was. Then in this case, again, when I set z to be a constant, I get a c squared. Okay, some c over here. Then this basically are equations of ellipses again. So these are a bunch of stacked up ellipses. And except in this case, the difference between these and the ones before is this comes to a point with the profile to be straight line. Why? Well, because if I were to set one of the variables 0, y to be 0, okay, that is I'm going to y0 is cut this surface with the plane y equal to 0. Here's the y-axis. Here's y to 0. If I cut this through this, what it's going to cut through is going to be a straight line on this surface. With the other one you can see in the back. Okay. Why? Because what I get is the equation z is equal to x squared over a, and z, and then you take the square root. Basically, is x is equal to some z is equal to some constant times x. And that's a straight line. That's a boundary. Okay. That's what the profile looks like, as opposed to the profile for instance, of these. You see why? Because in this case, if I were to set y, if I were to set y to 0, let me see which way I want to cut. If I set x 0, yeah, it doesn't matter. Then you wind up y. Basically, you get a square root plus 1 plus minus plus some z squared over c squared. Basically, you get a square root or a, in this case, hyperbola for the outline. Well, not square root. I mean, basically, if you set one of the constant, basically you get this hyperbolic. Is set one of the x equal to 0, then you get a hyperbola. That's what I'm trying to say. So you can tell the outline by setting the coordinate plane to be 0 to see which way you're looking at. Then finally, we have the saddle points. Okay, that's the case where you do not get sum of square. And this one, we will examine it by taking slice by slice of trace. Or you can do it by level curve. So over here, we set x equal to a constant, and we'll produce a series of trace. And if you set x equal to a constant, you get these second degree parabola pointing downward. As c gets bigger, the parabola gets higher and higher along the when the number, which number gets bigger? When x gets bigger. Yeah. When x gets bigger, then the c gets bigger, then the parabola gets bigger and bigger. That's why in these x planes, so when x gets bigger, you get a parabola keep rising higher and higher. Downward parabola. Okay, c minus y. And if you draw the series parabola out and then you can trace, then you can say, oh, this trace a series parabola comes down and then goes up. If you want to figure out what's the other two directions, you set y to be a constant, then you see they are a series of, for y equal to a constant, then you arrive at a series of parabola as the trace pointing upward. And putting these two things together, and these we call the saddle shapes. Okay. And that's it. Those are the classification of the quadric surfaces, basically all of them. And we use these as a guideline for studying, to making an example of computation for the future the stuff about surfaces. Because these are the easiest surfaces to calculate. Besides the plane, there's nothing much interest. It isn't very interesting. It's all flat. And to really look, to have some insight into the surface, we need something we can calculate. And these are the simplest one we can do. That's why the quadric surfaces are very important. Okay, that's it. And have a good day. And see you next time.